Voyager 1 crossed the final boundary of our sun's protection in 2012, and what it found on the other side should unsettle anyone who imagines humanity venturing beyond our solar system. The galactic cosmic ray count surged. The magnetic field shifted direction. The solar wind that had accompanied the spacecraft for 35 years vanished entirely. Voyager entered a realm where the sun's influence means nothing, where radiation from ancient supernovae floods every cubic centimetre, and where the nearest safe harbour is a star system over 4 light-years away. What lies beyond our solar system is not adventure, it is exposure. If you enjoy journeys into the deepest truths about our universe, hit that like button and subscribe. It means more than you know and helps bring more stories like this one to life. Now, with all that being said, get yourself comfortable. Let's begin. There is a machine out there right now, tumbling through absolute darkness, more than 15 billion miles from the warmth of the sun. It weighs less than a small car. Its main antenna is 12 feet across. Its body is roughly the size of a compact sedan, with a long boom extending outward, carrying magnetometers and a nuclear power source that is slowly, irreversibly dying. This machine was built in the 1970s using technology less powerful than the processor inside a modern musical greeting card. It was designed to study Jupiter and Saturn. It was expected to function for 5 years. It has been operating for nearly half a century, and it is still talking to us from a place no human object has ever been before. Voyager 1 launched on September 5, 1977, from Launch Complex 41 at Cape Canaveral, Florida. A Titan IIIe Centaur rocket punched it through Earth's atmosphere and set it on a trajectory toward the outer planets. Its twin, Voyager 2, had actually launched 16 days earlier, on August 20th, but on a slower path that would carry it past all 4 gas giants. Voyager 1 took a faster, more direct route, swinging past Jupiter in March of 1979 and Saturn in November of 1980. After its encounter with Saturn, Voyager 1's planetary mission was effectively over. It had photographed the Great Red Spot in detail never seen before. It had discovered active volcanoes on Jupiter's moon Io. It had studied the intricate ring system of Saturn and made the first close observations of Titan's thick orange atmosphere. But instead of shutting down, Voyager 1 kept going. There was nothing to stop it. The gravitational assist from Saturn had flung the spacecraft upward out of the plane of the planets, heading away from the sun at roughly 38,000 miles per hour. No engine fired to slow it down. No course correction aimed it at a new destination. It simply continued along the trajectory that gravity and engineering had prescribed, moving outward, second by second, mile by mile, year after year, into regions of space where nothing human had ever ventured. Voyager 2 followed a different path but the same ultimate fate. After visiting Jupiter, Saturn, Uranus, and Neptune, completing the only grand tour of all 4 outer planets in history, Voyager 2 also headed outward. Its trajectory carried it in a different direction from its twin, angled southward relative to the plane of the solar system. By the late 1980s, both spacecraft had completed their planetary encounters and entered what NASA designated the Voyager Interstellar mission. The new objective was simple in concept and staggering in ambition. Keep flying, keep measuring, find the edge of the sun's influence, and tell us what lies beyond. The distances involved are difficult to process with a human brain. Voyager 1 currently sits approximately 163 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Multiply that by 163. The result is over 15 billion miles. Voyager 2 trails at roughly 137 astronomical units, approximately 12.5 billion miles out. Both spacecraft continue moving outward at speeds that would cross the entire United States in about 5 minutes. But that barely register against the scale of interstellar distance. At 15 billion miles, the Sun is no longer the blazing disk that dominates our daytime sky. From Voyager 1's position, the Sun would appear as a very bright star, perhaps the brightest in its sky, but fundamentally a point of light rather than a sphere. The warmth is undetectable. The gravitational pull, while still technically present and still bending the spacecraft's path by immeasurably small amounts, has long since ceased to be the dominant influence on Voyager's daily experience. The solar wind, the stream of charged particles that has accompanied the spacecraft for its entire journey, no longer flows past its instruments. That wind ended. That is the story. Voyager 1 and Voyager 2 are the most distant human-made objects in existence. Nothing else is even close to competing. Pioneer 10 and Pioneer 11, launched in the early 1970s, preceded the Voyagers into deep space but stopped transmitting decades ago. Pioneer 10 sent its last weak signal in January of 2003. Pioneer 11 fell silent even earlier, in September of 1995. Both spacecraft are still out there, drifting, but they are mute. They carry no functioning instruments. They send no data. They have become inert metal, tumbling through the void without purpose or voice. New Horizons, the spacecraft that flew past Pluto in 2015 and later visited the Kuiper Belt object Arakoth, remains active and is heading outward. But it sits far closer to the Sun than either Voyager, at roughly 60 astronomical units. It has not yet approached the termination shock, let alone the heliopause. It will be decades before New Horizons reaches the boundary region, and its instruments were not designed for the same measurements the Voyagers carry. In the hierarchy of human exploration, the Voyagers occupy a category that contains only themselves. They are the scouts, the first emissaries, the only machines that have physically touched the medium between the stars and reported back what they found. But to understand what they found, you first have to understand what they crossed. And this is where most public descriptions of the Voyager mission become dangerously imprecise. When news headlines declared that Voyager 1 had left the solar system, they were using a phrase that is scientifically misleading. The solar system, defined by the Sun's gravitational dominance, extends enormously farther than Voyager has travelled. The Oort cloud, a vast theoretical shell of icy bodies loosely bound to the Sun by gravity, is believed to begin at roughly 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units. Voyager 1, at 163 astronomical units, has not even reached the inner edge of this structure. At its current speed, it would take approximately 500 years to arrive at the Oort cloud's inner boundary, and roughly 30,000 years to pass through the cloud entirely. Beyond the Oort cloud, the Sun's gravitational influence continues, weakening with distance according to the inverse square law but never truly reaching zero. The gravitational sphere of influence of the Sun, the region where its pull dominates over that of neighbouring stars, extends roughly 1 to 2 light-years outward, depending on the mass and proximity of nearby stellar systems. The nearest star, Proxima Centauri, lies about 4.24 light-years away. Voyager 1 is currently less than 1 light day from Earth, which is roughly 1/365th of a light-year. It has covered less than 0.1% of the distance to the nearest star. By the definition of gravitational dominance, Voyager is still very much inside the solar system and will be for tens of thousands of years. So what did Voyager actually leave? It left the Heliosphere, and this distinction is not a technicality, it is the entire point. The Heliosphere is the region of space controlled by the solar wind, a continuous outflow of charged particles ejected from the Sun's corona at speeds ranging between 300 and 800 kilometers per second. This wind carries with it the sun's magnetic field, stretched and twisted by solar rotation into a vast spiraling structure. As the wind flows outward, it inflates an enormous bubble around the sun, pushing against the pressure of the interstellar medium, the thin gas and dust and magnetic fields that fill the space between stars. Where the outward push of the solar wind balances the inward pressure of the interstellar medium, a boundary forms. That boundary is called the heliopause. It is the outermost edge of the sun's direct physical influence on its surrounding environment. Inside the heliopause, conditions are shaped by the sun. The magnetic field is solar. The dominant charged particles are solar wind ions. The radiation environment is modulated by solar activity. The 11-year solar cycle governs how many cosmic rays penetrate inward, how strong the magnetic field is at various distances, and how far the solar wind extends before it decelerates. Outside the heliopause, the sun's control ends. The magnetic field becomes galactic in origin. The particle population shifts from solar wind ions to galactic cosmic rays and interstellar plasma. The radiation environment is no longer governed by our star, but by the accumulated violence of the Milky Way. Supernova remnants, neutron star magnetospheres, and particle acceleration processes operating on scales that span thousands of light years. This is the boundary Voyager crossed. Not the edge of the solar system in the gravitational sense, not the departure from the sun's family of planets and comets and asteroids, but something arguably more significant, the edge of the sun's protective influence, the point beyond which the sun can no longer shield anything from the full force of the galactic environment. The crossing did not happen all at once. It happened in stages, and the story of how NASA confirmed it is one of the most painstaking detective stories in the history of space science. Voyager 1 first encountered the termination shock in December of 2004 at a distance of approximately 94 astronomical units. The termination shock is the inner boundary of the heliosphere's edge region, the point where the supersonic solar wind abruptly slows to subsonic speeds as it begins to feel the back pressure of the interstellar medium. Crossing this boundary was itself a major discovery. The distance was farther from the sun than some models had predicted, and closer than others. The shock was not a smooth, symmetric shell, but an uneven, fluctuating surface that Voyager passed through multiple times as the boundary rippled back and forth across the spacecraft's position. Voyager 2 crossed the termination shock in August of 2007, at a distance of approximately 84 astronomical units, 10 astronomical units closer to the sun than its twins crossing. This asymmetry revealed something important about the heliosphere's shape. It is not a perfect sphere. The heliosphere is compressed on the side facing the direction of the solar system's motion through the interstellar medium and elongated on the trailing side. The Sun and all its planets are moving through the galaxy at roughly 230 kilometers per second. The interstellar medium rams into the heliosphere from that direction, squeezing the boundary closer to the Sun on the leading side. Voyager 1 exited on the upstream side. Voyager 2 crossed on the flank. The different distances confirmed that the heliosphere is a dynamic, asymmetric structure shaped by the interaction between the solar wind and its galactic surroundings. Beyond the termination shock, both spacecraft entered the Heliosheath, the thick, turbulent buffer zone where the slowed solar wind piles up, heats, and churns before reaching the heliopause. This region proved far stranger than anticipated. The magnetic field in the Heliosheath was chaotic, with field lines folding back on themselves and forming magnetic bubbles that trapped and released energetic particles unpredictably. Temperatures rose to more than 100,000 Kelvin as the kinetic energy of the solar wind converted into thermal energy upon deceleration. The Heliosheath was a zone of transition, neither fully solar nor fully interstellar, a no man's land where two vast physical systems pressed against each other. Then, in the summer of 2012, Voyager 1's instruments began registering the final transition. The low-energy charged particle instrument and the cosmic ray subsystem, two detectors that had been faithfully counting particles for 35 years, showed a dramatic shift. The flux of anomalous cosmic rays, particles accelerated at the termination shock within the heliosphere, dropped precipitously over just a few days. Simultaneously, the count of galactic cosmic rays, high-energy particles from outside the solar system, surged upward. The crossover was stark. The solar particle population vanished. The galactic population arrived. The Sun's contribution to the local particle environment dropped to essentially zero, but the magnetic field data complicated the picture. Scientists had expected that crossing the heliopause would produce a sharp rotation in the magnetic field direction, a clean switch from the solar field orientation to the interstellar field orientation. Instead, the field direction changed gradually, over a period of days to weeks. Some researchers argued this meant Voyager had entered a new, unexpected transition region, not quite inside the heliosphere, but not truly in interstellar space either. Others argued the spacecraft had crossed the heliopause, but that the boundary was more complex than simple models predicted. The debate played out in journals and at conferences throughout 2012 and into 2013. The resolution came from an unexpected source: plasma oscillations. In early 2012, a powerful coronal mass ejection erupted from the Sun. This massive burst of solar plasma and magnetic field raced outward through the heliosphere at speeds exceeding 1,000 kilometers per second. Months later, the shock wave from this eruption reached Voyager 1's location, more than 120 astronomical units from the Sun. When the shock wave arrived, it caused the plasma surrounding the spacecraft to vibrate at specific frequencies. Voyager 1's plasma wave science instrument, one of the few instruments still receiving enough power to operate, detected these oscillations clearly. The frequency of plasma oscillations depends directly on the density of the surrounding material. Higher density produces higher frequency. When scientists analyzed the oscillation data, they calculated a plasma density of approximately 0.08 electrons per cubic centimeter. This was roughly 40 times denser than the plasma density in the outer heliosheath. The measurement was decisive. Voyager 1 was immersed in material far too dense to be solar wind plasma. It was surrounded by the interstellar medium. Working backward through the particle data, the magnetic field records, and the plasma wave measurements, scientists pinpointed the crossing. Voyager 1 had passed through the heliopause on or around August 25, 2012, at a distance of approximately 121.7 astronomical units from the Sun. The announcement came in September of 2013, more than a year after the actual event. For those 13 months, Voyager 1 had been in interstellar space, and no one on Earth had been certain. Voyager 2 confirmed and expanded the discovery 6 years later. On November 5, 2018, at a distance of approximately 119 astronomical units, Voyager 2 crossed the heliopause in a different direction. Its crossing was in some ways even more scientifically valuable than its twins. Voyager 2 still carried a functioning plasma science instrument, the PLS, which directly measures the properties of charged particles in the surrounding medium. Voyager 1's equivalent instrument had failed in 1980, nearly 4 decades before the heliopause crossing. Everything Voyager 1 knew about the plasma around it had to be inferred indirectly from plasma wave oscillations. Voyager 2 could measure the plasma directly, providing density, temperature, speed, and composition data that Voyager 1 simply could not. The PLS confirmed what the plasma wave data had suggested. At the heliopause, the solar wind plasma disappeared abruptly. One moment, Voyager 2 was immersed in outward-flowing solar material. The next, that flow had ceased entirely, and the spacecraft was surrounded by a denser, hotter, and essentially stationary plasma of interstellar origin. The transition was sharp. The contrast between the two environments was unambiguous. Two spacecraft, two independent crossings, two complete sets of instruments recording the same fundamental transition from different directions and at different times. The scientific case was airtight. The heliosphere has a definable outer boundary. That boundary can be crossed, and beyond it lies a physical environment that is measurably, fundamentally different from everything within the Sun's domain. These machines are old. Their power sources are decaying at a rate dictated by the 87.7-year half-life of plutonium-238. Each Voyager's 3 radioisotope thermoelectric generators produced about 470 watts of electrical power at launch. Today, they produce roughly 220 watts, and that number drops by approximately 4 watts every year. NASA has been systematically shutting down instruments and heaters to conserve what little power remains. The cameras were turned off in 1990. Science instruments have been deactivated one by one. Thruster firings to maintain antenna pointing toward Earth have become less frequent and less reliable as the hydrazine fuel ages and the thruster valves stiffen. The radio signals reaching Earth from Voyager 1 carry a power of roughly 23 watts at the source, transmitted through a 12-foot dish antenna aimed at a planet more than 15 billion miles away. By the time those signals reach the 70-meter dishes of NASA's Deep Space Network, the received power has fallen to roughly 1/10 billionth of a trillionth of a watt. That engineers can extract meaningful scientific data from a signal this feeble is a testament to decades of refinement in deep space communication techniques. But even this capability has limits. The round-trip light time for communicating with Voyager 1 now exceeds 45 hours. A command sent from Earth takes nearly 23 hours to arrive. The spacecraft's response takes another 23 hours to return. A single exchange requires nearly 2 full days of waiting. Within the next few years, sometime in the late 2020s or early 2030s, the power will no longer sustain any science instrument. The last heater will shut down. The last data stream will go silent. Voyager 1 and Voyager 2 will become inert objects, still racing outward at their current speeds, still carrying their instruments and their golden records, but no longer capable of sensing or reporting their environment. They will become artifacts, drifting through the interstellar medium on trajectories that will carry them past distant stars over the coming tens of thousands of years. Voyager 1 will approach within about 1.6 light-years of the star, Gliese 445 in the constellation Camelopardalis, in approximately 40,000 years. It will not slow down. It cannot slow down. It will pass through that star's neighborhood and continue onward, a silent messenger from a civilization that may no longer exist. But before the silence comes, the data has arrived, and that data describes something that no Earth-based telescope, no theoretical model, no computer simulation had ever fully captured. Voyager measured the actual conditions in the space between stars, not inferred, not modelled, measured, particle by particle, field line by field line, oscillation by oscillation. What the instruments revealed was not the serene emptiness that most people picture when they imagine the void between star systems. The interstellar medium is not nothing. It is something. It has density, temperature, magnetic structure, and a radiation environment governed by the violent history of the galaxy. It presses inward against the heliosphere from all directions. It carries the fingerprints of supernovae that exploded millions of years ago. It contains particles that have been bouncing through the Milky Way for longer than our solar system has existed. And the heliosphere, the bubble that has sheltered every planet, every moon, every living cell, and every spacecraft in human history, holds all of it at bay. When Voyager crossed that boundary, it left the only protection it had ever known. It entered a realm that the sun cannot reach, cannot warm, cannot shield, and cannot control. The crossing was quiet. There was no visible flash, no audible alarm, no shudder in the spacecraft's frame. The heliopause is not a wall. It is a transition in the properties of the medium, a change in who controls the local environment. One moment the sun was in charge, the next, the galaxy was. Voyager registered the change in its particle counters, its magnetometers, and its plasma wave receiver. It noted the shift in the only language it knows, numbers transmitted as radio pulses across 15 billion miles of space, and waited patiently for someone on Earth to decode what it had found. What it found demands that we understand the structure it left behind. The heliosphere is not merely a boundary on a chart. It is a shield, a dynamic one, constantly rebuilt by the sun's continuous exhalation of charged particles. To grasp why Voyager's crossing matters so profoundly, we need to understand how that shield works, what it protects against, and why losing it changes absolutely everything about the nature of the space environment. That understanding begins with the sun itself, with the million-degree corona that cannot hold on to its own atmosphere, and with the relentless wind that blows outward in every direction at every moment of every day. The heliosphere exists because the sun cannot stop exhaling, and everything alive in this solar system depends on that single, continuous breath. Every second, without pause, without interruption, without any possibility of being switched off, the sun is losing mass, not slowly, not gently. 4 million tons of matter convert into pure energy every single second through nuclear fusion in the solar core. But that is not the mass loss that concerns us here. The sun also loses roughly 1.5 million tons of material every second through a completely different process. This material does not vanish into energy, it leaves. It physically departs the sun's surface and races outward into space as a continuous stream of charged particles. Protons, electrons, and heavier ions, torn from the solar corona by temperatures so extreme that gravity cannot hold them, fly outward in every direction at speeds that range from 300 to 800 kilometers per second. This is the solar wind, and it is the single most important factor protecting every object in our solar system from the full hostility of the galaxy. The solar wind begins in the corona, the outermost layer of the sun's atmosphere. The corona presents one of the most enduring puzzles in solar physics. The surface of the sun, the photosphere, has a temperature of roughly 5,800 Kelvin. The corona, which lies above the surface, somehow reaches temperatures exceeding 1 million Kelvin. This is like walking away from a campfire and finding that the air 10 feet away is 1,000 times hotter than the flames themselves. Scientists have proposed numerous mechanisms to explain coronal heating, including magnetic reconnection events called nanoflares and the dissipation of magnetohydrodynamic waves propagating upward from the solar interior. The precise balance of processes remains an active area of research, but the consequence is settled fact. The corona is so ferociously hot that the sun's gravity cannot contain it. At 1 million degrees and above, the thermal energy of coronal particles exceeds the gravitational binding energy at the sun's surface. The result is an outward boiling of material that never stops. Protons and electrons, stripped from hydrogen atoms by the intense heat, stream outward in a supersonic flow. The wind is not uniform. It emerges faster from coronal holes, regions where the sun's magnetic field lines open directly into space, and slower from regions where closed magnetic loops temporarily trap material before releasing it. The fast wind can exceed 700 kilometers per second. The slow wind averages around 300 to 400 kilometers per second. Both carry embedded magnetic field lines from the sun, frozen into the plasma by the high electrical conductivity of the ionized material. As the sun rotates, approximately once every 27 days at its equator, These embedded magnetic field lines get wound into a vast spiral pattern. This is called the Parker spiral, named after the physicist Eugene Parker, who predicted the existence of the solar wind in 1958, years before it was directly measured by spacecraft. The Parker spiral creates a three-dimensional magnetic structure that extends outward through the entire solar system. Every planet, every asteroid, every comet, every grain of interplanetary dust sits within this spiraling magnetic web. It is the skeleton of the heliosphere, the structural framework upon which the sun's protective bubble is built. The wind carries this magnetic structure outward at enormous speed. At Earth's distance, 1 astronomical unit, the solar wind arrives roughly 4 days after leaving the sun. By the time it reaches Jupiter at 5 astronomical units, it has been travelling for about 2 weeks. At Neptune's distance of 30 astronomical units, the wind has been in transit for roughly 4 months. And it keeps going. Past the Kuiper belt, past the scattered disk of icy bodies, past the region where the last known large objects orbit. The wind flows onward into increasingly empty space, growing thinner as it spreads across an ever larger volume, but never fully stopping until something stops it. That something is the interstellar medium. The space between stars is not truly empty. It contains a thin but measurable population of gas and dust, threaded by a magnetic field of galactic origin. This material exerts pressure. Not much pressure by any standard a human would recognize, but enough to matter over the enormous distances involved. The interstellar medium pushes inward against the heliosphere from all directions. The solar wind pushes outward. Where these two pressures balance, the heliopause forms. But the transition is not a simple boundary. It occurs in stages, and understanding those stages reveals the heliosphere's true complexity as a protective structure. The solar wind leaves the corona at supersonic speeds, meaning it travels faster than the speed at which pressure disturbances can propagate through the medium. As it flows outward, it gradually thins. The density drops with the square of the distance from the sun. At Earth's orbit, the wind density is roughly 5 to 10 particles per cubic centimetre. By the time it reaches 30 astronomical units, at Neptune's distance, the density has dropped to roughly 1/10 of a particle per cubic centimetre. At 60 astronomical units, it is thinner still. But the wind remains supersonic, still outrunning its own pressure waves, still flowing freely outward. Then, at roughly 80 to 100 astronomical units from the sun, depending on solar activity and the local properties of the interstellar medium, the wind hits the termination shock. This is the point where the interstellar medium's inward pressure becomes significant enough to force the solar wind to decelerate abruptly from supersonic to subsonic speed. The transition is violent in physical terms. The kinetic energy of the wind converts into thermal energy. The material heats dramatically. Temperatures in the post-shock region can exceed 100,000 Kelvin. The wind does not stop. It slows, compresses, and heats, like air piling up in front of a moving vehicle, but at a scale that spans the entire solar system. Beyond the termination shock lies the Heliosheath, the thick, turbulent buffer zone where the decelerated solar wind piles up. Here, the decelerated solar wind accumulates in a turbulent, magnetically complex region that can extend 30 to 50 astronomical units farther outward. The Heliosheath is where the sun's last stand occurs. Solar material piles up. Its magnetic field lines compress and fold, and the outward pressure gradually dissipates until it can no longer overcome the inward push of the interstellar medium. At the outer edge of the Heliosheath, the Heliopause marks the final boundary. Beyond it, the solar wind does not flow. The sun's magnetic field does not organize the local environment. The heliosphere ends. The heliosphere is not a perfect sphere. The solar system's motion through the local interstellar medium compresses the bubble on the leading side and likely stretches it into a tail on the trailing side. Voyager 1 and Voyager 2 exited through different regions of this asymmetric structure, which partly explains why they crossed the heliopause at slightly different distances from the Sun. Now, the critical question: why does any of this matter for protection? The answer lies in what the heliosphere keeps out. The galaxy is saturated with cosmic rays. These are not electromagnetic radiation like visible light or radio waves. They are physical particles, mostly protons but also helium nuclei, heavier atomic nuclei, and electrons, traveling at velocities that approach the speed of light. The energy of individual galactic cosmic ray particles spans an extraordinary range. At the low end, cosmic rays carry energies of a few million electron volts, comparable to particles produced in medical equipment. At the high end, the most energetic cosmic rays ever detected carry energies exceeding 100 billion electron volts, concentrated into a single subatomic particle. A proton at that energy carries the kinetic energy equivalent of a professionally thrown baseball compressed into a space smaller than an atomic nucleus. These particles originate from the most violent processes in the Milky Way. Supernova remnants are the primary source. When a massive star explodes at the end of its life, the resulting shockwave expands outward through the interstellar medium at thousands of kilometers per second. This shockwave persists for thousands of years, gradually decelerating but continuously accelerating charged particles trapped in the magnetic turbulence at the shock front. A process called diffusive shock acceleration allows particles to bounce back and forth across the shock boundary, gaining energy with each crossing. Over thousands of years, this mechanism produces protons and heavier nuclei, with energies spanning many orders of magnitude, from modestly energetic to spectacularly extreme. Other sources contribute as well. Pulsars, the rapidly spinning neutron stars left behind after certain supernovae, generate intense rotating magnetic fields that can accelerate particles to high energies in their magnetospheres. Binary star systems, where material transfers between companions produce shocks and magnetic environments capable of particle acceleration. And at the largest scales, the supermassive black holes at the centers of active galaxies generate jets of relativistic plasma that produce the highest energy cosmic rays observed. Particles so energetic they may originate from other galaxies entirely and travel across millions of light-years of intergalactic space before reaching the Milky Way. The flux of galactic cosmic rays in interstellar space, as now confirmed by Voyager's measurements, is substantial. It represents a continuous rain of high-energy particles arriving from all directions, generated by violent events spread throughout the galaxy's history. Some of these particles have been traveling through the interstellar medium for millions of years, scattered and redirected by the tangled galactic magnetic field, their original source long since faded into a cold remnant or dispersed entirely. The heliosphere blocks the majority of these particles from reaching the inner solar system. The shielding mechanism is electromagnetic. Galactic cosmic rays are electrically charged. When a charged particle enters a magnetic field, it experiences a force perpendicular to both its velocity and the field direction. This force curves the particle's path. In the complex, turbulent magnetic environment of the heliosphere, incoming cosmic rays encounter a constantly shifting maze of magnetic field lines carried outward by the solar wind. Lower energy cosmic rays, which have smaller momenta and are more easily deflected, get scattered repeatedly. Their paths become randomized. Many are turned around entirely, reflected back into interstellar space before they penetrate to the inner solar system. Higher energy cosmic rays with greater momentum are harder to deflect. Some punch through the heliosphere's magnetic barrier and reach Earth's vicinity, but even these are partially moderated by the journey through the turbulent magnetic field. The effectiveness of this shielding varies with the solar cycle. During solar maximum, when the sun is most active, the solar wind is stronger, The magnetic field is more intense and more disordered, and the heliosphere inflates slightly. Cosmic ray suppression increases. The flux of galactic cosmic rays reaching the inner solar system drops measurably. During solar minimum, when the sun is quieter, the wind weakens. The magnetic field becomes more orderly and less effective at scattering particles, and more cosmic rays penetrate inward. This 11-year oscillation in cosmic ray intensity is one of the most reliably measured phenomena in space physics, tracked continuously by ground-based neutron monitors and space-based particle detectors for over 70 years. The quantitative impact of heliospheric shielding is significant. Estimates based on both modeling and direct measurement indicate that the heliosphere reduces the galactic cosmic ray flux, reaching the inner solar system by approximately 70 to 75% compared to the unshielded. Interstellar value. For lower energy cosmic rays, those below roughly 1 billion electron volts per nucleon, the suppression is even more dramatic. The heliosphere effectively excludes the vast majority of these particles, reducing their flux by factors of 10 or more. Only the most energetic galactic cosmic rays, those above roughly 10 billion electron volts, pass through the heliosphere with relatively little attenuation. This is not a minor effect. It is the difference between a radiation environment that permits complex chemistry and one that systematically destroys it. Galactic cosmic rays interact with matter in ways that are fundamentally different from the lower energy solar radiation that dominates inside the heliosphere. When a high-energy cosmic ray proton strikes an atomic nucleus in biological tissue, it does not merely ionize a few atoms along its path. It can shatter the nucleus entirely, producing a shower of secondary particles, neutrons, protons, pions, and heavier fragments that spread damage across a wide area. A single galactic cosmic ray heavy ion, such as an iron nucleus traveling at nearly the speed of light, can destroy every cell along its path through tissue. The resulting DNA damage is qualitatively different from that caused by lower energy radiation. It involves clustered lesions, multiple simultaneous breaks in the DNA double helix that are far more difficult for cellular repair mechanisms to fix. The biological consequences of chronic galactic cosmic ray exposure are a primary concern for space agencies planning missions beyond low Earth orbit. Astronauts aboard the International Space Station, which orbits within Earth's magnetosphere and well inside the heliosphere, receive a radiation dose roughly 10 times higher than the average person on Earth's surface, mostly from trapped radiation in the Van Allen belts and from the fraction of galactic cosmic rays that penetrate the heliosphere and Earth's magnetic field. Even this modest cosmic ray exposure is carefully tracked and limited by mission duration constraints. A crew traveling beyond the heliosphere would face the full, unshielded galactic cosmic ray flux. The radiation dose rates in interstellar space, based on Voyager's particle measurements extrapolated through standard radiation transport models, would substantially exceed the annual limits currently imposed on astronauts by every major space agency. Over a multi-decade interstellar transit, the cumulative dose would pose severe risks including elevated cancer rates, cardiovascular damage, cataracts, and potential central nervous system effects including cognitive decline. These are not speculative concerns. They are direct extrapolations from measured particle fluxes using well-established radiation biology. But the heliosphere's protective role extends beyond shielding biological tissue. It also protects the chemical environments on planetary surfaces and in planetary atmospheres. Consider Mars. The red planet lacks a global magnetic field and possesses only a thin atmosphere. Without the heliosphere, the full interstellar cosmic ray flux would bombard the Martian surface continuously. The increased radiation would accelerate the radiolysis of any subsurface water ice, breaking water molecules into hydrogen and oxygen through radiation-driven chemistry. It would increase the production of oxidizing compounds in the Martian soil. It would make the surface even more hostile to organic chemistry than it already is. The heliosphere does not make Mars habitable, but it reduces the radiation load on the Martian surface by a substantial margin, preserving at least the possibility of subsurface environments where liquid water might persist without being chemically destroyed by radiation. The same logic applies to the icy moons of the outer solar system. Europa, Enceladus, Titan, and other bodies with potential subsurface oceans exist within the heliosphere's protection. The cosmic ray flux at their distances from the Sun is already higher than at Earth's orbit, because the heliosphere's shielding is less effective in the outer regions. But it is still substantially lower than the full interstellar value. If these moons orbited a star with a weaker stellar wind and a smaller heliosphere, the cosmic ray bombardment of their ice shells would be more intense, potentially affecting the chemistry of their subsurface oceans over geological time. Even in the inner solar system, the heliosphere's absence would be noticeable. Earth's own magnetic field provides a second layer of protection, deflecting most charged particles that make it past the heliosphere, but the magnetosphere is not impregnable. During geomagnetic storms, when the Earth's magnetic field is disturbed by solar activity, cosmic ray access to the upper atmosphere increases temporarily. If the background cosmic ray flux were 3 to 4 times higher due to the absence of heliospheric shielding, the baseline radiation dose at Earth's surface would increase. The effect at sea level would be modest, perhaps a 10 to 20% increase, because the atmosphere provides yet another thick layer of shielding. But at aircraft altitudes, in low Earth orbit, and especially on the surface of the Moon, which lacks both atmosphere and magnetic field, the increase would be substantial. The heliosphere also mediates the interaction between the interstellar medium's magnetic field and the magnetic environments of individual planets. Inside the heliosphere, each planet's magnetosphere interacts primarily with the solar wind. The solar wind compresses the dayside magnetosphere and stretches the night side into a long magnetic tail. This interaction is dynamic but relatively well characterized after decades of study. If the heliosphere vanished and the interstellar medium's magnetic field directly impinged on planetary magnetospheres, the interaction would change in ways that are difficult to predict precisely. The interstellar field has a different orientation, a different variability pattern, and potentially different plasma properties than the solar wind. Earth's radiation belts, which are populated by particles trapped in the magnetosphere through solar wind interactions, would reconfigure. The auroral zones would shift. The shielding effectiveness of the magnetosphere itself might change. But here is the part that most people never consider, the part that transforms the heliosphere from a permanent fixture of our solar system into something far more fragile and contingent. The heliosphere has not always been the size it is today. It is not a static shell. It responds to the conditions it encounters as the solar system moves through the galaxy, and those conditions have changed dramatically over Earth's 4.5 billion year history. Right now, the Sun and its planets are passing through a region of the interstellar medium called the local interstellar cloud, a relatively warm, moderately dense patch of partially ionized gas roughly 30 light-years across. The properties of this cloud determine the external pressure pushing against the heliosphere. The density of the local interstellar cloud is approximately 0.1 to 0.3 particles per cubic centimeter, and its temperature is roughly 6,000 to 8,000 Kelvin. These are the conditions Voyager measured just outside the Heliopause. They are the conditions that currently define how far the heliosphere extends. But the local interstellar cloud is not the only structure in our galactic neighborhood. The solar system is located near the edge of this cloud, and within the next few thousand to tens of thousands of years, it will likely exit into a different region. Some models suggest the Sun may enter an area of lower density material, which would allow the heliosphere to expand. Other models suggest the Sun could encounter a denser cloud, which would compress the heliosphere inward. The galactic environment is not uniform. It is patchy, clumpy, and variable. And as the solar system orbits the galactic center at 230 kilometers per second, it passes through these patches on timescales that are short compared to geological history. Scientists have found evidence that this has happened before, with measurable consequences. Studies of deep-sea sediments and Antarctic ice cores have detected anomalous concentrations of the isotope iron-60, a radioactive atom produced in supernova explosions and delivered to Earth by interstellar dust. Elevated iron-60 levels have been found in sediment layers corresponding to periods roughly 2 to 3 million years ago, and again around 7 to 8 million years ago. These deposits suggest that the solar system passed through regions of enhanced interstellar material during those epochs, potentially debris from relatively nearby supernovae that temporarily increased the density of the local interstellar medium. A denser interstellar medium would compress the heliosphere. If the external pressure increased sufficiently, the heliopause could be pushed inward from its current distance of roughly 120 astronomical units to perhaps 60 or 70 astronomical units, or even closer. At those distances, the outer planets would remain inside the heliosphere, but the shielding for the entire solar system would be reduced. The termination shock would move inward. The heliosheath would thin. The magnetic barrier that deflects lower energy cosmic rays would weaken. More galactic cosmic rays would penetrate to the inner solar system, increasing the radiation dose on every planetary surface and in every planetary atmosphere. A 2024 study published in the journal Nature Astronomy explored a more extreme scenario. Researchers modeled what would happen if the solar system encountered a particularly dense cold cloud, one with a density of roughly 1,000 to 3,000 particles per cubic centimeter, far denser than the material currently surrounding our heliosphere. Under those conditions, the heliosphere could be compressed so dramatically that it would shrink inside Earth's orbit. Our planet would be directly exposed to the interstellar medium. The galactic cosmic ray flux at Earth's surface would increase by roughly an order of magnitude. The interstellar material itself, including hydrogen, gas, and dust, would interact with Earth's magnetosphere and upper atmosphere in ways that could alter atmospheric chemistry and climate. The researchers suggested this may have actually occurred roughly 2 million years ago, correlating with geological evidence from the same period. Ice core data shows a notable increase in cosmic ray indicators during that epoch. The timing overlaps with the beginning of a series of glaciation events in Earth's recent geological history. Whether the heliospheric compression directly contributed to climate change remains debated and unconfirmed, but the physical mechanism is sound. More cosmic rays reaching the atmosphere can increase cloud nucleation, affecting cloud cover and planetary albedo. Changes in atmospheric chemistry from incoming interstellar gas could modify the greenhouse effect. The connection between heliospheric size and planetary conditions is not speculative. It is a matter of magnitudes and timescales. This variability transforms the heliosphere from a permanent feature into a conditional one. It exists because the sun produces a wind, yes, but its size and effectiveness depend on what that wind pushes against. Change the external conditions, and the shield changes with them. The protection we enjoy today is the product of a specific, temporary equilibrium between a specific stellar wind and a specific interstellar environment. Shift either variable, and the calculation changes. The solar system has orbited the galactic center roughly 20 times since the Sun formed. Each orbit takes approximately 230 million years and carries us through different regions of the galactic disk. Some orbits pass through spiral arms where supernova rates are higher and the interstellar medium is denser and more turbulent. Other segments of the orbit carry us through the quieter interarm regions where conditions are calmer. The heliosphere breathes in response, expanding during quiet passages and contracting during turbulent ones. Earth's cosmic ray exposure has fluctuated accordingly, rising and falling on timescales of tens of millions of years in a rhythm dictated by our galactic orbit. Some researchers have proposed correlations between these cosmic ray fluctuations and mass extinction events in the geological record. Though these correlations remain tentative and controversial, the statistical evidence is suggestive but not definitive. What is definitive is the underlying physics. The heliosphere can change size. The cosmic ray flux at Earth can change. And the driver of that change is not anything happening within the solar system, but the conditions the solar system encounters as it moves through the galaxy. This realization adds a layer of vulnerability to the story that transforms the heliosphere from reassuring to sobering. We are not simply protected, we are conditionally protected. The heliosphere is not a fortress. It is a tent, erected by the solar wind, held up by the continuous outpouring of charged particles from the corona, and pressed upon from all sides by an interstellar medium whose properties we do not control and cannot predict with certainty. The tent holds today. It has held for billions of years, with variations, but it is shaped by its environment, and that environment is not static. None of this will happen during the Sun's remaining main sequence lifetime, in the sense of the heliosphere vanishing permanently. The Sun has roughly 5 billion years of hydrogen fuel remaining. As long as it burns, the solar wind will blow and the heliosphere will exist in some form. But the heliosphere is not eternal, and it is not fixed. When the Sun eventually exhausts its hydrogen and evolves into a red giant, its outer layers will expand enormously. The nature of its wind will change, and when it finally sheds those layers and collapses into a white dwarf, the wind will cease. The heliosphere will dissipate. Whatever remains of the solar system will be exposed to the full interstellar medium for the first time since the Sun ignited 4.5 billion years ago. Other stars face this reality on different timescales. Massive stars burn through their fuel in millions of years rather than billions. When they explode as supernovae, their heliospheres, often called astrospheres, are destroyed instantly. The planetary systems around those stars, if any existed, are suddenly exposed to the interstellar medium while simultaneously being engulfed by the expanding supernova remnant. The radiation environment changes catastrophically. But even stars on the main sequence vary enormously in their heliospheric protection. Red dwarfs, which constitute roughly 70% of all stars in the Milky Way, are small, cool, and produce relatively weak stellar winds. Their astrospheres may be significantly smaller than the Sun's heliosphere. Some models suggest that habitable zone planets orbiting red dwarfs sit so close to their host star that they remain within the astrosphere, but the margin is thin. A particularly active phase of the interstellar medium, perhaps a passing shock from a nearby supernova, could temporarily compress the astrosphere and expose those planets to enhanced cosmic ray fluxes. This means that heliospheric protection is not a universal feature of planetary systems. It depends on the host star's mass, age, activity level, and the properties of the local interstellar medium. Some planetary systems in the galaxy may exist with heliospheres that are barely effective. Their habitable zone planets would experience cosmic ray fluxes several times higher than Earth's, with consequences for atmospheric chemistry, surface radiation, and the long-term stability of complex organic molecules. The heliosphere is not a luxury, it is infrastructure. It is the invisible architecture that makes the interior of our solar system a fundamentally different environment from the galaxy at large. Without it, the conditions that permit complex chemistry, stable atmospheres, liquid water, and biological evolution would be degraded. Not necessarily destroyed, life is remarkably resilient, but significantly compromised, and it is not permanent. It is contingent on the Sun's output, on the density of the interstellar medium we happen to be passing through, and on the galactic environment that changes beneath us like weather we cannot forecast and cannot control. And this is what makes Voyager's crossing so consequential. When Voyager 1 passed through the Heliopause on August 25, 2012, it did not simply cross a line on a chart. It left the only environment in which human civilization, human biology, and human technology have ever operated. It entered a place where the sun offers nothing. No warmth, no light to speak of, no magnetic shielding, no wind to push back the cosmic rays. Voyager crossed from protection into exposure, from the conditional safety of the tent into the full force of the storm that has been raging outside for as long as the galaxy has existed. Most people, when they think about the challenges of space travel, think about distance. They think about the years it would take to reach another star, the fuel required, the loneliness of the journey. These are real challenges, but Voyager's data reveals a challenge that is in many ways more fundamental. It is not merely the distance that makes interstellar travel so daunting. It is the nature of the environment that fills that distance. The interstellar medium is not a passive void to be crossed. It is an active, irradiated, magnetically structured medium that must be endured. And enduring it requires protection that the sun can no longer provide once you leave the heliosphere.